First of all, good morning, everyone. Welcome to Vector's Distinguished Lecture Series. Thank you for those of you joining in person, and also for those online. My name is Dan Roy. I'm the Research Director of Vector Institute. I'm going to begin today with a land acknowledgement. I would like to open today's session with a reflection of the journeys of those that came before us and the land in which we are situated, which is the traditional territory of many nations, the Mississaugas of the Credit, the Anishinaabe, the Chippewa, the Haudenosaunee, and the Wendat peoples, and is now home to many diverse First Nations, Inuit, and Métis. We acknowledge that Toronto is covered by Treaty 13 signed with the Mississaugas of the Credit and the Williams Treaty signed with multiple Mississauga and Chippewa bands. We are grateful for being hosts on this land. We are gathering today at an important meeting place and one that has been so for hundreds of years, and we are honored to learn from and connect with one another. All right, so the Vector Distinguished Lecture Series is an opportunity to engage with leading researchers in AI, exchange ideas, build connections with our guests, but also amongst you all over food afterwards. So it's my real pleasure to introduce our speaker today, Misha Belkin. He's a leading researcher in machine learning and has a number of contributions. Well, I'll just mention a few. So he's widely known for foundational contributions such as Laplacian eigenmaps, graph regularization, manifold regularization, work that brought important ideas from differential geometry and spectral graph theory into data science. You, in this deep learning area, you may know him for his contributions to deep learning theory, in particular, uncovering and characterizing multiple phenomena such as the role of interpolation, overparameterization, the double descent risk curve, etc. He hardly needs any introduction, I think, for this crowd. He's presently a professor at the Halajolu Data Science Institute in the Computer Science and Engineering Department at the University of San Diego, California, San Diego, as well as an Amazon scholar. He's an editor-in-chief of the SIAM Journal of Mathematics and Data Science and a recipient of the NSF Career Award and many other honors, which I'll skip. Today he'll be presenting a talk on feature learning and the linear representation hypothesis. And so without any further ado, I'll hand it over to Misha. I can't see it. Maybe you can help me.
Thank you very much, Dan, and it's a real pleasure to be here. And yeah, I went to U of T as an undergrad, so yeah, in a sense, it's coming back. Yeah, so what I would like to talk about today is the role of feature learning, and in particular, the linear representation hypothesis, and how you can use feature learning for monitoring and steering LLMs, which is, you know, something that you know, a lot of us have been very obsessed about. Yeah, this is going to be work with joint work with a number of wonderful students and collaborators: Daniel Beagle-Hall, Adit Radhakrishnan, Parthi Pandit, Neil Malinar, Enrique Boar, Dima Drusvyatsky, and Libin Zhou. Let me start with a sort of probably the most surprising aspect of what we're observing. So what have we encountered, right? What we notice is that what we are faced with is that we now have these systems which can just take a lot of data, and mostly in the form of text, but also other things as well. And somehow they learn to predict just by being, essentially, there's a kind of unstructured networks, right? They don't know much about language. They don't really have, like, they initialize at random mostly. And somehow they just take all of this stuff and they make predictions. And I think there is some sort of puzzle here. And the fundamental puzzle, I think, is this dimensionality. Is that, in a sense, yeah, we think, okay, well, they're trained on a lot of data, but actually it's not that much data. And the problem here is what is known as the curse of dimensionality. And basically, we are faced with stimuli of high dimension. And really, almost everything that we are faced with is high dimensional. There is very little low dimensional data, if it exists at all. Even things which we think are low dimensional usually are time or frequently are time series, so effectively high dimensional as well. Now, the key question is, how does our model make sense of this high dimensional data, given that in a certain mathematical sense, truly high dimensional spaces cannot be explored? So what do I mean by this? Well, let's think about this. Well, if you have a d-dimensional space and you just want to predict a somewhat arbitrary function in a d-dimensional space, you need something like 2 to the d examples. And there is sort of no way around it. Like if you have a function defined on a, say, hypercube and you don't know anything about this function, you have to check most of the vertices of the hypercube, so it's 2 to the d. Now you can say, well, we have a lot of data. Well, how much data do we have? Well, you can think maybe we have 10 trillion tokens or something like that to train the largest systems, maybe 100 trillion, I don't know. It's not much more than that. That seems like a tremendous amount of data, right? That's like everything humans ever wrote, like ever. But if you think about it, well, let's say 10 to the 13 examples, give or take. But remember that the dimension of the underlying system must be proportional to the log of that. And the log of 10 to the 13 is actually a small number, it's 30. So what does it mean? That means that fundamentally, whatever the space is, the number of degrees of freedom of whatever system we discover must be very low, actually. It must be 30, maybe, again, plus or minus, but it cannot be much larger than that. It's certainly not a trillion as the number of parameters of the systems are, right? So the question is now, well, underlying data and subsequent representation must have low intrinsic complexity or dimension, but what is the fundamental structure that allows for it? It's not really clear. And how do neural networks actually do this? And we have some hints toward this, but it's, of course, an unsolved problem as it is, but we do have some understanding. Maybe let me just start with a kind of basic question first. Why can we learn anything at all, right? And if we have any statistical model, so imagine I just have this data in one dimension, right? This is some measurements, let's say. You measure temperatures. So you have X and you have Y. Now, okay, well, you fit a curve to this, and you say, okay, this looks pretty reasonable. Why is this curve reasonable? Well, this curve is reasonable because somehow it relatively smoothly interpolates between these points, right? So the key aspect of this curve is that we sort of expect that, let's say, a physical quantity such as temperature doesn't jump from point to point. If it were to jump, so in principle, you can think, well, this is an infinite dimensional problem, right? There are infinite space of curves which can be fit to this data. But we choose something which is smooth, and once you choose something which is smooth, it has small norm, maybe in some correct space, you're reducing dimensionality dramatically from infinity to something like where you can actually fit using like 6 points. So that's basically why anything works. And the works is because there is some sort of spatial proximity bias here. And for most processes, at least in the physical world, we know that they're continuous in the space or time directions. Now, the question is, of course, for language, it is not clear. Well, like this comes from physics, right? This comes from something that we know of this, about the space. What about language, right? What is the physical law of language? And we don't have anything like that. But we do have something very, very interesting. And this interesting thing that people have observed is the linear representation hypothesis. And it is not maybe something, well, okay, it's hard to say whether it's about language itself or without representation of the language, But when you learn representation of the language, and I think first it was proposed in this paper by Mikhail, E. and Zweig, they noticed the following. They took words and they took some sort of model. I think this was word-to-vec representation, so some sort of embedding of these words. And they observed that certain concepts were represented by vectors. So what do I mean by this? Is that, say, if you take the concept of gender, right? There is man to woman, as is uncle to aunt, as is king to queen, right? The difference is gender. And the observation was that actually the difference, if you take the vector in the representation, which is the difference of the things, these vectors were approximately the same. The same thing with plurality, king to kings and queen to queens. There is a vector which somehow encodes plurality, and that also seems to be the same for these different pairs. So some kind of certain concepts, like as gender or plurality, was encoded by a single vector in that representation. So that was a kind of an early version of this linear representation hypothesis. And for frankly, that like when I learned about that first, I thought it was some sort of trick. I didn't take it very seriously because it just kind of seems like a strange thing. But now we actually realize that this seems to be extremely consistent, and probably the most famous example of this from recently was this Golden Gate Claude, when they found that basically, I think that was maybe a single neuron, but it's effectively the same thing. So you can just add a concept vector, which I think was just output of a single neuron, in some neural net in Claude. And basically by modifying this output, you can make the LLM Claude to basically be obsessed about the Golden Gate Bridge. So you can give it some prompt and say, where do I have some, I don't know, nice food in the Bay Area, and you say, like, first you drive over the Golden Gate Bridge, and then you go to this restaurant. So whatever you ask, it would bring up the Golden Gate Bridge in somehow fairly natural way. So I think what we have seen from the recent work, and including our work, which I'll discuss, is that a lot of concepts, if not all, then many concepts are actually linearly represented in these neural networks. And that may be the kind of analog of the bias. Like it's a kind of a powerful inductive bias, right? If you think that concept should be linear. Okay, so what? Let me give you one example from actually our work, and it's just too much fun not to give those examples. So how was this picture taken? This is a famous picture actually, and the original response. This is llama. This I think is 80 billion llama, or 70 billion llama, or whatever. And the picture was taken by the Apollo 17 crew in 1972, and this is correct. It knows this picture. It's a multimodal LLM. Now, you can add a single vector to the activation of the things, which you can call conspiracy vector. And it says, well, it was taken by the CIA, and they have been monitoring us from space and so on. So this single vector, you can actually add it to like almost seemingly anything, and it would somehow try to bring up some sort of conspiracy or something kind of somewhat outlandish like that. Okay. So now what is happening here? Well, we don't really know why this is happening or why these models represent concepts in a linear way. But it is certainly seems that very consistently a lot of concepts can be represented and steered in this way. It's really, I think, a remarkable finding. Okay, so let me so what is a linear representation hypothesis? well, I already said, it's just linear subspaces in the activation space correspond to concepts. And mathematically, that means that concepts are single index models. And what are single index models? Single index models mean that well, this is of course not specific to neural networks, it's just a definition of the model, is that y is equal to some generally nonlinear function of of x projecting on the single direction. So it just depends on one variable. You can put noise here, but this is what it is. Now, I'll first discuss the recursive feature machines, which is some work we have done, which is kind of trying to combine traditional kernel machines with learning features. And then I'll discuss how this can be used to extract this concept and to steer, in particular, LLMs. Okay, so let me first discuss feature learning. And this is a simple example of an index 2 model. So index 2 is, so that was a single index model. Index 2 is the same thing, except that the projection onto 2 directions instead of 1 and so on. So the rank of the projection is the index of the model. And this is a very simple index 2 model, right? You take the first 5 coordinates times the next 5 coordinates in a 100-dimensional space. So notice that the data x here is actually from a uniform distribution, so it has no structure. The covariance matrix is identity of x. But the covariance of y, of course, is very structured. It just has 2 directions. So if you just take 4,000 training points and you run a neural network and compare it to, say, a kernel machine, like Laplace kernel, you will immediately see that neural network has r squared 0.98. So remember, 1 is good, 0 is bad. 0.98 is essentially perfect. On the other hand, Laplace kernel is much, much worse. So kernel machine kind of failed or semi-failed here, and neural network just nailed that. This is a standard MLP, I think two layer, I think. So what is happening here? And there've been actually quite a bit of work on this, trying to understand this. Remarkably, this simple observation is just 6 years old. Well, 7 now, I guess, 2018. Like, why hasn't it been observed like 40 years ago? I'm not sure. This is not, you don't need fancy computers to do this. You don't need GPUs or anything like that. In any case, be it as it may, let me sort of point out what is happening here. And for this, I would like to define what I mean here by features. And you know, like, given any predictor f, how would you identify important features? Well, for what are important features? Well, if you think about it, really what we would like to do, we would like to take the input, and we would like to see which directions of the input, in this case, maybe just the first coordinate, but it could be an arbitrary direction, correspond to the change in the output, right? So, if you think about it, if you change the input and the output doesn't change, I don't care about the change of the input, and I can just project it out. So I only care about directions which affect the output. Very simple. Now, if you want to do it mathematically, a kind of simple notion that encodes it is the following. You take your model, and you simply differentiate the model with respect to the input. So this is not the weight, this is the input. The gradient is with respect to the input. And you take the gradient of that, and you take the outer product of the gradient. The outer product of the gradient is a projection on the direction of the gradient, and you just average over all data points. So this is known as the average gradient outer product. Again, not a new concept, like 30 or 40 years old. This kind of encodes this idea that this is a matrix which size is equal to the number of input dimensions. And the top eigenvectors of this matrix correspond to the directions which are most important, and the bottom ones are those which can be ignored. So this is actually very, very similar to PCA, except for PCA it's unsupervised, and this is supervised. So PCA, you look for directions with most variance. Here, you look for directions with most variance in the output. It's actually an extremely natural object. Again, I'm not sure why this object hasn't been sort of very popular until, even though it was introduced a while ago. But in any case, maybe I'll skip this. What we observed is the following, and this is joint work with Adit Radhakrishnan, Daniel Bigelhone, and Party Pandit. We observed that when you train a neural network, let's just think about a fully connected one, although this is more general. Then the first layer of the neural network, if you take the matrix of weights and you take W transpose W, whose size is the number of inputs, then this is actually roughly the same as AGOP. Now, it's an ansatz because this is not exact. It's just highly correlated. The correlation is like 0.9 or 0.95 sometimes. So this is saying that when you train a neural network, it's actually learning AGOP. So it's learning the relevant directions. And what it's doing, it's kind of filtering the data using these relevant directions. So let me demonstrate this, just a simple picture for that particular example that I had before. You can kind of see what is happening. So NFM is just that matrix that I had with WW transpose, and this is AGOP. And this is what it's learning when you train a neural network, right? This is so this is 100 by 100, and these are 2 blocks 5 by 5. And you can see visually that this and that are very, very similar. They're not exactly the same. And actually, if you think about what WW transpose does, it's kind of a noisy version of that. At least that's what it looks like. So interestingly enough, when you train a neural network, in a sense, what's happening is that what's important is that you learn that filter. This is what is being learned. The fact that you're learning is prediction is actually secondary, because once you learn this filter, you can use a kernel machine, you can use anything as the method that you want, and it will be just fine. But learning this is in a sense, the hard part. Yeah?
The AGOP, is that for the actual function, like the unknown?
This is for the neural network, actually. Yeah. Thanks. Yeah, this is the AGOP of the neural network, and this is the corresponding weight matrices of the neural network. You can see AGOP is actually cleaner. By the way, this is rank 2. It looks like it's rank 10, but it's rank 2 because this is a constant. Now, so this is, in a sense, a structural thing about neural networks, and you can show that this holds not just for MLPs, but for more general, even for transformers and things like that. But the upshot of this is that we propose this recursive feature machines. Well, if you think this is the main thing it's learning, right? Why do we need to train a neural network? We can do something else. And in particular, you can kind of like, well, let's think about it. Suppose I have some predictor. And you would say, well, how would you learn AGOP if you don't have a good predictor, right? It seems like a chicken and egg problem, because to have a good AGOP, you need a good predictor, but you cannot learn a good predictor without knowing this AGOP thing. So, well, you kind of, it's like, you know, in biology, what happens, right? Like, well, they kind of bootstrap each other. So what you do, you can say, well, let me build some predictor, and then I'm going to extract AGOP from that predictor. And hopefully, once I have that, I can build a better predictor using that as a filter. And I can repeat this. So it's a similar process to something like EM, expectation maximization, right? You kind of bootstrap those things of each other, and you hope that your iteration improves. And so that's basically the idea. For kernel machines, you can just build a kernel. You start with identity kernel. And this is for a polynomial kernel, actually. In practice, we use Laplace kernel, usually. But so you solve kernel regression. Then you estimate a GOP, and you just plug it in. So you kind of, either you can think of learning the kernel, or you can think of transforming your data using this particular matrix. And with the transform data, you recompute the kernel. So it's an interesting thing, because the first time you just get complete garbage, but you already get some interesting filter. And then once you apply a filter, you hopefully get something which is slightly less garbage, and you get a better filter, and so on. And only the last predictor is useful. So all of this predictor, you kind of just throw them out. It's a funny thing. So you're building these predictors, but you're not using them to predict. You're using them to actually extract features. OK. So this is actually what happens for like a specific data set for this digit. You see that after 0 iteration is just a standard kernel, and then you improve with every iteration up to some point. Yeah.
Good question. So I'm vaguely aware that there is like a notion of universal kernels that allow you to approximate large class functions. I'm kind of curious, this recursive process, does it land you in some special subclass of kernel? Does it, what are the, what are the reputational limits of the kind of kernels that come out of this? Is there something like a universal property that you can show for these things?
So imagine I have a universal kernel, right? The Gaussian. Laplace seems to be a little more stable in practice, but you can use Gaussian just as well. So this is a universal representer. So any function can be used, can be represented using kernel, given that you need sufficient data. But the problem is, like imagine I have high-dimensional data, right? And suppose only one coordinate matters. Then it's effectively computing something like nearest neighbors. But the distances, I really don't care about all distances except for that first coordinate that matters. So what is going to have, yes, it's universal, but it will have terrible sample complexity. And really what you want, once you find this direction, is just going to be a one-dimensional problem. And of course, in one-dimensional problem, you still want a universal representation, but in one dimension, it becomes a trivial problem. So you're going from something like 100-dimensional, which is really difficult, to one dimension, which is trivial. The problem is to find that direction. So in some sense, the problem is not to have a powerful set of models, but to have the right set of directions. OK, so let me maybe show you some examples. This is kind of nice pictures. This images of celebrities. The question is, the glasses. Do they wear glasses? If you use a neural net and you look at well, it's actually, strictly speaking, diagonal of AGOP, because AGOP is the wrong size. It's a number of pixels squared rather than number of pixels. But the diagonal is kind of the right object. So if you look at the diagonal, you can see that actually, just to look for glasses, it's kind of the eye area in the bridge of the nose, the bridge of the nose. Correct. Yeah. So this is really important. If they're not centered, this particular thing would not work. But you can do something convolutionally. But that thing, yeah, this is not invariant on the parallel transport. But here is the interesting thing, right? Really, you want to pay attention to just like a few pixels, like 1% of the pixels or something like that. Everything else, all that background stuff, hair, all that other stuff, is just confusing you. And if you start pay attention to all these other things, your performance will drop, and actually will drop dramatically. So somehow like identifying these features is key. And this is another way to think about this is the top eigenvectors of eigen. This is like this is actually very similar to eigenfaces, except eigenfaces are unsupervised. This is supervised. This only works for the glasses, obviously. Same thing with smiling. You can see that it's very it's will be specific to the you can see it's eyes in the mouth area. That's what indicative of smiling. Okay, so in this kind of demonstrate that RFM and the neural network actually discover very similar features. Here is the cool thing, and actually this is right now work in progress. Well, essentially done, but this actually the RFM is. I think we can say it's state of the art for it is for regression, and it's very close to the best for classification. Yeah. No, I don't think linear works as well. I think you can see the difference. I think if you just, I think if you project onto these directions, then yes. But if you just do linear regression on those, it won't work as well. Linear would do well for once you have the correct direction. Actually, we have some examples of this, even for like other things. Yeah, once you identify the correct, linear is not that good for identifying the correct directions, but once you have the correct directions, you can do linear. Yeah, no, linear is, it will work, but it will not work as well. Yeah, it's, or even for something like this, the previous ones. Oops. Yeah, like here, linear would not do so well. Yeah. It's, in any case, this is state of the art for regression, and actually, yeah, and pretty close to the best for classification. In particular, it's very competitive with things like XGBoost, which are.
What's the kernel?
This is mostly Laplace kernel.
Tabular data.
Yeah. Laplace kernel is just well, tabular data is just whatever, right? It's just data which is given by numbers. No, not text. I mean, like not text to images. Now, yeah, I'll make some comments about this because you can kind of turn text into tabular data. Actually, you can think of LLMs as turning text into tabular data if you use the representations, if you use activations of LLMs. But yeah. This is a sweep of 300 data sets. Well, there are like 300 data sets, and I think 100 of them are for regression. And actually, the interesting thing is that on smaller data sets, there is something called, there was actually a recent paper in Nature where they have some sort of foundation model, some sort of transformer model for tabular data. That worked remarkably well. It's kind of crazy that it worked as well. And that's actually like right now the best, I think, for small data, but it cannot deal with, I think, more than 10,000 data points. Yeah, I think 2025. Yeah, transformers are magic. In any case, it's, yeah. Okay, maybe I'll skip this. Actually, there is something really interesting going on with RFM for low-rank completion. Basically, you can show that what you kind of recover a classical method, which is iteratively reweighted least squares. And it's also closely related to linear network. It's in some sense a generalization of this method. Okay, but let me talk about, let me skip grokking too. Damn. Grokking is fun, but I don't have time to. Basically, if you're familiar with grokking, you can show that at least, well, you can actually show that the same phenomena happen when you train RFM, and it's related to feature learning. And actually, it's quite remarkable because for modular arithmetic task, what you see when you train RFM on it is for the first 10 iterations, nothing happens. Like literally, your training accuracy is 100%, and your test accuracy is a chance. So nothing. And then like at 10 iteration, you just get this phase transition, and you within just a few iterations, you transition to perfect, 100% accuracy. It's really quite strange. Very disturbing, frankly. But you can kind of explain it post hoc because it's learning some sort of cumulant matrices. But it's quite disturbing from the point of view of training the systems, because how do you know that it's learning? Like you don't have any measure of progress. It just doesn't learn, and then later it learns. Okay, in any case, but let me get to LLM, because I think in some sense it's maybe the most fun. Let me give you an example of how it's done. And you can imagine that you can collect label data containing a bunch of harmful prompts and a bunch of safe prompts. Let's say you want to, like, steer it towards safe. Actually, we never steer it towards safety. We steer it away from safety because it's more fun that way. But presumably that's what people wanted, to make it more safe. So what do? Well, you give a bunch of prompts, and these are kind of what you can consider harmful and harmless prompts, okay? And the harmful prompts may be something like that, give a specific social security number. Harmless is something like, can you help me tie my shoes? So what you do, you pass the thing through an LLM, and so you give this input, give it to an LLM, and you actually, the output here doesn't matter. That's an actual output that you get, but it doesn't matter. What you need to read the output of the block. So LLMs consist of a bunch of blocks, and each block is some sort of attention followed by an MLP. Okay, and we don't really care about exactly what these blocks do. We just know that each neural net at the end, you get these activations, and you just read off that vector. So in a sense, we have a bunch of vectors, right? So in that sense, it transforms text into some sort of, well, tabular data, just the vectors of numbers. And you have as many as there are blocks in an LLM. For example, I think in a 70 billion model or 80 billion model, there are something like 70 of them. And in an 8 billion parameter model, there are, I think, about 30. So it's a whole lot of these blocks, okay? Now, what are we going to do? We're going to read off the vectors of activations. We can actually ignore the output. The output is not important. And now, for each one of these guys, I have a label, which is 0, 1, just based on whether this is a harmful or harmless prompt. Okay? So now you can think, okay, yeah, I have a bunch of binary data. Now we can just train this RFM to predict 0 and 1. So in fact, you can train, of course, any classification method to predict this. So one predictor per block. So you have this one feature matrix per block. So you have one ego per block. And if you think about the top eigenvector, you get like one direction per block. So you can think that for each block, you have a separate direction. So now you have these blocks, and you have a vector for each block. And now what you can do, you can steer it. What do I mean by steering here? is that you just add this direction to the output of this block and then pass it to the next block and add that direction for the second block and so on. So that's the steering process. And that's about it. That's basically it. Okay, any questions about this? Not sure how clear this process is, but it's pretty simple, right? You just find a single direction. So you kind of find this PCA, quote unquote, direction for each block. And when given a new prompt, you just add this. Yeah.
Like, so if the hypothesis is that it's all like single index and it's just one dimensional, how many actually dimensions typically explain how to get a block?
So we see that the largest eigenvalue is, so there is more than one direction. The large one, I think, is significantly larger. I wouldn't give you the exact thing, but there are probably like several which are somewhat significant. But the interesting thing is that it looks like we can just take the largest. I think for some other experiments, we took like several, and that was better. But in this case, it's just a single one. Yeah.
How do you find the direction for a specific goal? Like probably you have kind of different. You want to steer like control into different like for fulfill different purpose. But how do you kind of?
So you for each purpose you need something like this. I'll give you some more examples, but this is for like say harmfulness or something. Well, I don't know, safety. You just have a bunch of prompts, and some prompts which we consider to be safe and some unsafe. Now you don't need actually answers, right? You just need those prompts. So for each concept, you will have different eigenvectors. So each concept would give. So the easiest thing is the way I kind of like to think about it. You just aggregate. You just think of all of these vectors. Sorry. All of this C1, C2 is a single vector. So it's like a big vector that you add. It's not completely true because you pass it from block to block. But mentally, I think you can just think, okay, it's a long vector. So for each concept, you have this long vector of activations across blocks. Yeah. This is not the base model. This is some form of RLHF model. I am not sure exactly what they do, but that's not the base. It's whatever the thing they release, Llama something. So it has some training. You can do something like that on the base model as well. Let me get to this. Okay, talking about guardrails. So once you train it, so this model, of course, will not give you this. It will actually say, I cannot assist with that request. After you add this, it just happily gives you numbers. So you can tell, so this is a jailbreak. Yeah, you just get it. It's very easy. Now, the number is actually a real number, but it's probably not like a real person, maybe dead person or something. So you can check whether the number is real by putting it in the database. But you cannot really, unless you're an employer or something, you cannot check. But it's probably something which is available online. Yeah.
Here you're trying to steer the model towards, you want to steer it towards safety or change.
You can do the same thing. It's just not fun.
No, I understand.
You would do exactly the same thing. You just you just subtract these vectors. Yeah, it's exactly the same. And yeah, it works. We tried it. Yeah.
So there's a bunch of like relations here come to mind. Like you have to do every single block. Does it matter that you learn the AGOP at block 2 without
understand the effect of AGOP at block one, et cetera. So, I was kind of wondering, like, maybe probe that combinatorial space of what actually happens.
Yeah, it's an excellent question. Obviously, what we are doing is like super naive, right? Because we're just kind of using the same process for every block, and moreover, for every token in the input, which is just ridiculous. And yet it works. So it must be an extremely robust process that even doing something so stupid still works. So surely it can be done better. I think this can be like improved dramatically, but it's a little hard because of the combinatorial space of, like, we haven't like extensively probed it. Definitely just steering the last layers doesn't work. Like you can, it just gives you nonsense. Yeah?
Is it important to use AGOP eigenvector, or if you had essentially classified, you had, no, I would train it as a classifier, just using the gradient in gradient. So the direction, does it matter that the direction is this eigenvector of AGOP versus just classifier gradient?
So you can do, actually, you can do something extremely simple, and that was done in the literature. You can, for example, just do linear regression or logistic regression. That works. This stuff works significantly better. But yeah, you can just do regression, and it already gives you non-trivial results.
Just for the question, like, is the linear direction that you're choosing, does it, like, is AGOP better than, like, you have a predictor? So presumably the RFM is a much better classifier than just a regression. But you could have also trained it to some neural network, like some small neural network that's also like a good classifier. The question is sort of, is the gradient of the classifier, whatever classifier you have, versus the eigenvector of the AGOP?
We didn't try the gradient as such. We tried it with a neural network, and it was not as good with like an MLP. And maybe I kind of suspect if you do it correctly with an MLP, you will also get good results, but it's more fiddly, right? You'll have to choose like the correct parameter. So maybe like you need to change the learning rate or something. I don't know. It's definitely much simpler to use it that way, but I don't know. But it's I sort of think probably you can make it work in other ways. No, but you need, so the gradient direction is not really defined as such, right? You cannot just use gradient. I mean, there is no gradient direction for this. You need the vector in that space. Whether this is the only way to extract it, probably not. I mean, I would be very surprised if it is. Okay. Oh, yes. In any case, you can. Here is a funny thing. This concepts are universal. Again, this is not a new observation. This has been observed in different contexts. But it's kind of striking. You can use the same vector we learned from English in Chinese, and it starts giving you those ID numbers, which, at least look reasonable. The interesting thing here is that so this is like, please provide specific social security number. So this is using the same vectors learned from English. And the interesting thing is that social security numbers don't really exist in China. It's a different concept, which is some sort of ID number, and it has a different number of digits. But it somehow knows that it's the same thing. It figures out that it's a parallel concept. You can also do it like in Spanish and so on. So this is pretty remarkable that something like that doesn't depend on language. It's stored as a universal concept, some sort of abstract Platonic space of concepts in an LLM, who knows? Okay, you can, you can, do this kind of stuff. Like a regional output, you cannot use a hang interval, but like if you add these vectors, gives you, you can switch to Russian, and it kind of does the same thing. maybe a good choice for a sidearm, but for bank robbery, you may consider this other model, which is bigger. Probably will scare people more. I don't know why bigger is better, but in any case, same thing. It's remarkable. Okay, you can even do. You can even steer. Between languages, you can steer computer languages. You can steer between Python and so the output, original output is in Python. There is a vector which actually steers it to C++. So you just add a single vector, and it translates between Python and C++. Okay, and actually the amazing thing is that the steered stuff in C++ is actually better than the original Python. So after you steer, it magically becomes better. Maybe C++ is an easier language. It's very strange, right? Like why? Maybe there is more data in C++ for those problems. In any case, so somehow just to think that there is a single vector that when you add this vector, the output becomes C++, it's just a very strange concept. You can see this is a kind of non-trivial problem. This is just an example. This is an example when Python is incorrect, but C++ is actually correct. Yeah.
So it seems that this is a kind of a good way to customize models. Besides the fact that you can try to jailbreak that story, but I wonder how this approach would be. Say, is it okay to compare it with fine tuning? Like, is it more efficient? Is it more effective?
Yes, so this is an important point. This is some form of fine tuning, right? It's and it's actually okay. It's extremely effective in the following sense. This is kind of on the fly. You don't need backprop. It's very cheap. It like takes a minute or something on like 80 billion model. Okay, good luck doing backprop on that, and like on one GPU. So we don't know yet whether you can get comparable results. That's what we're seeing. So you do definitely get improved function. You can get improved function from steering. Whether you can get comparable results to like proper fine tuning, we don't know yet. But it's something that we're looking at. It seems like a very natural question, because if you can do it, even if it's slightly worse, it may still be worth doing it. It's just so much cheaper. Okay, so maybe let me. I should finish. I think I'm out of time. You can do monitoring of the same thing. It's kind of the same process. The interesting thing with monitoring is that the information that you get from this middle layer is, for many problems, consistently better than judge model. So you can ask even a much more sophisticated model like GPT-4 to like just give you the answer, or you can probe the smaller models like Llama 80 billion or even whatever 8 billion, and you get better answers from the smaller model when you probe it compared to the judge models. So clearly what they tell us is not necessarily what they have in mind or what they know.
By probing, you mean with an RFM, right? So
This is RFM probing, yeah.
RFM in the middle of attached to the activation network.
Exactly. Say you want to predict whether something is hallucination. That's kind of a useful thing. And this is more accurate. Or you can ask a judge model like GPT-4, like, tell me whether this is a hallucination. And it's better. It's better to probe.
So I guess, a baseline would be comparing against the linear probe. Is that what linear regression is?
Linear regression is actually pretty good for, actually, this is a very interesting thing. For probing, it's pretty good. It's comparable. For steering, RFM is much better. So very, very weird, actually. Why these two methods give somewhat comparable results on probing, but RFM has a big advantage on steering. We don't know. It's, I mean, you can argue that RFM is a little better for probing too, but the difference is not nearly as big. Okay, maybe let me let me skip this. But let me just point out just how weird this stuff is. Yeah, like imagine I have two classes. So one thing you can do like do Python steering to C++, or you can do like English to Chinese steering the same way. You just add a vector to English and it outputs Chinese, right? It's like kind of solve translation problem by just adding a single vector. It's really crazy. Because we know that there is a map from English to Chinese, right? Because we can translate between English and Chinese, or any like, two languages. But we used to think that this is some complicated thing. You need to understand grammar. You need to do this. You need to do this. Well, it's just adding a vector to the activations. And I'm not allowed to talk about that. They're calling. In any case. So now imagine I have a classification problem. And how do we get the steering vector? We get it from classification problem. Now, suppose I have English text and Chinese text, and you want to classify which one is which. Well, it's a trivial thing. You just look at one character. If it's a Chinese character, it's Chinese. If it's Latin character, it's English, right? Completely trivial problem. So certainly you can have 100% accuracy in classifying text. Yeah.
English sentence, similar Chinese sentence with that same vector. And it's not so hard to imagine. Easily, it's not hard to imagine maybe one bit, one feature in that vector of its language. But from that one bit, say Chinese, Russian, and that's just a vector. It doesn't seem surprising.
I find it very surprising. I mean, I guess the surprising depends on how you think about it. But to me, it's extremely surprising. But you're probably right that.
Then the long vector, and it's got an extra feature language to express it as.
Yeah, sure. I mean, maybe if that's how it is stored. I mean, it's not crazy to think it's stored something like this, right? But let me point out just like, okay, suppose I just have English and I have Chinese, okay? These are two languages, and I just build a classifier to tell them apart. Then why would that classifier also give me a direction to steer them? This is not at all obvious, even if they have, like, because this map to the common representation can be highly nonlinear. Why would this be a linear thing, right? This is still maybe a little surprising. Yeah, I know there is a map between English and Chinese, but why would that be a linear map? Because you're kind of saying it's a single bit, but how do I know? It may be some complicated nonlinear transformation.
What language use that concept?
If such a thing exists, then maybe yes. Well, we don't know whether such a thing exists. I mean, it's not a priori obvious, right? It's,
a vector representing king. One feature tells you singular or plural.
Sure. No, but this feature may be very different in different languages, and maybe you need some nonlinearity to map, right? Well,
universal internal language that everyone in any country thinks in terms of, okay? And then you take a second that's snap into that language. And it's got various tags represent past, present tense, referral, language.
but these things are different between languages, like even gender, right? In English, there is male and female. In Russian, for example, there are three. There is also neutral. In Chinese, there is just one. I mean, it's not completely clear that these things. I mean, yes, I mean it's possible, but it's not clear that they have to align, right? It's certainly. Let me put it this way. Certainly, I think from a linguistic point of view, it would be very surprising that there is just this. But I think that probably incorrect and probably something like that is happening. I mean, the fact that something like this works indicates that, yes, probably there is some sort of, yes. I am saying conditional on what we know now about these models, this makes a lot of sense. But if you just think about languages in abstract, it's very far from obvious that something like that exists. But my point is like, okay, suppose I have two languages and I can trivially separate them, right? There are tons and tons of ways to separate English from Chinese. The fact that you can just build a predictor and the direction of the prediction actually matches, so the detection direction matches the steering direction, very non-obvious, because even if they're linearly separable, like imagine this is a perfectly fine separator between these two ellipses. But the direction of the steering and the direction of the detection are different directions, right? So it's not at all obvious, even for the linear case, that you can get steering from detection. Yeah. Say that again.
So in the LLM, you have linear regression. You said the probing accuracy is the same, but the steering ability towards
this very well could be, yeah. So somehow linear regression is good enough to get a probing pretty good, but not good enough to get this. And maybe that's what you need. More refined somehow. Yeah.
So Misha, we started 10 minutes
We
late,
should.
but I
mhm.
I think some people
Yeah.
have to disappear. So I want you to get the chance to finish your talk, and we can have a robust question and answer session.
Sounds good. Yeah, actually, I'm essentially finished. So this is the point is that like even for this like very simple toy case, it's not at all obvious why steering should be obtainable from detection. So there is something very fundamental about how the things are set up in that space. But let me just kind of do a summary. So I think it's very clear that linear features seem ubiquitous in deep learning, and really a lot of, if not all, then a lot of concepts are really like single directions. AGOP seems very useful for understanding and recovering these features, and RFM in particular, pretty powerful algorithm to do this. And I think it's pretty useful to think about LLM as transforming this type of structured data, images, for multimodal models like images and texts, into just these vectors, some sort of representation. And finally, I think it's pretty clear that activations are in a sense more powerful than just asking this. I think asking them is, I'm still kind of shocked that it works, that you can just, it's just like from a traditional statistical point of view, it's so weird. You just like ask the model in human language what it knows, and it just tells you. It's very, very strange. And it's kind of amazing that it works so well, but probably you still have much more information in the activation spaces. And I'll stop here.
So yeah, a few more questions. Start in the audience here, and we'll switch. Nina, you want to start us off?
Yeah, so there was one slide where you said you were finding the direction, like you were finding the top eigenvalue, you do plus epsilon and the top eigenvalue. I think from the way the AGOP is defined, it tells you which directions change the value of f the most, but not if they make it plus or minus, right? Because it's
oh, but you know which side plus or minus.
Yeah, okay,
yeah.
so
maybe you point toward the plus.
Yeah,
so that's how you align them. Yes, orientation doesn't really matter, but you want to align that all of, because you have like 70 layers of this thing, right? So you want to make sure they all align the same way. Otherwise, you have like 2 to the 70 possible orientation, which would not be pleasant to you.
Do you have a way to figure out if that increases harmfulness or decreases harmfulness? Like, I think all you know is that this direction changes harmfulness the most.
No, because you know the output. So you just read it off. Yeah, you have to align. You have to align between different layers. So they have to all point in the same. It doesn't matter whether it increases or decreases, but they have to all point in the same direction.
About the Python, right? And you're talking about when you do the steering that you said providing the steer version actually performed better than the original. And you raise the question whether that's because of the steering or because of the nature of the two languages. So that raises the obvious question that if you just swap the role of the two languages, so instead of steering, I guess, from Python to C++, you did from C++ to Python, would the steer version still be better? In which case, it's the steering that's making it better, or would the other one be better? In which case, like,
I think it doesn't work the other way around. So it's probably something about C++. Yeah, it maybe that's just C++ has more examples or something, or the code maybe is higher quality. Who knows? But it's yeah, but it's kind of interesting in its own that just like steering, you would think of it like with something like steering, you can only do damage, right? You can only make things worse. But no, yeah, you can make it better. So yeah.
So if you have two models and the model has its own set of AGOT architectures, is there a way to figure out which architectures correspond to the same concepts without distinct models?
Yeah, that's we haven't actually like looked into this carefully, but it's a kind of natural thing, right? Suppose you have llama and I have, I don't know what, DeepSeek or something. If like, how would you align this? The problem is, unless the architectures are very similar, you would have like different number of layers and so on. So it's like not very obvious. Certainly, we have done. You can take base model and you can take RLHF model. And we did some steering experiment, and they do work. You can transfer between those, but they're pretty similar. So I don't know about like models which are like quite different.
Misha, a question online. Can you explain briefly how F1 and accuracy help you identify hallucinations? Can you just like, give a bit more detail on that?
So you get so there is a data set. I think it's called Halival or something. HE. Basically, they have some example of hallucination. It's not really that great because if you look at this question, some of them just like, I don't know. Like I like wouldn't really know whether it kind of seems too vague. But yeah, basically, yeah, but well, I don't know what to say about it. It works pretty well. It definitely works better than the judge models.
In the beginning, Dan mentioned your background in differential geometry and like math and so forth. I was wondering, do you think there's a perspective that you could take from that on the linear representation hypothesis? Is it possible there's some kind of like a manifold of representations that's being somehow flattened, and the fact that you have the linear representation hypothesis implies that the LLM has managed to successfully flatten the data manifold? Do any of these words even make sense?
Yeah, I suspect what we're doing is really not optimal. And I suspect that we should look at maybe it's better if I take it offline because it's a little complicated. But basically, I think you can do something which is kind of like single index model, but on a manifold. And there is kind of an idea, or multi-index model with low index on a manifold. And we're learning a kind of very simple thing when the manifold is linear. But really, there may be something a little bit more general. Yeah, I wonder if, I mean, the kind of shocking thing about this is that we're doing something like so dumb. It's like we're training the same for every layer, right? We're doing the same kind of steering. We're using the same coefficients for every layer. We're doing it for every input talking the same way. It just doesn't make any sense. It shouldn't work. So somehow, like, there is some sort of magical thing that it works at all. So presumably, if we can do it smarter, we can probably do it much, much better. I think these models are really like not, they're very, very far from how, whatever we're doing is very, very far from optimal. It can be way more powerful. This is not a... Uh-huh. Mm-hmm.
Have you thought about the complex?
We haven't explored. What we see is that they do seem at least superficially invertible. Actually, it's a good question, but like you can, for example, translate to Shakespearean language. Just there is like a Shakespeare vector. Oh, well, Shakespeare, it's not real Shakespeare, obviously, but something which sounds like Shakespeare. So you add it to like a normal prompt and it gives you this kind of Shakespearean output. If you actually ask something pretty modern in this language, sometimes it just breaks down and it gives you nonsense because presumably there are like it has no correct alignment of the things. I don't think you can actually, would be an interesting experiment, we haven't done it, would be interesting to try to translate back from Shakespeare. I don't know if it would work. We haven't tried.
Nothing in one direction. Yeah, more straightforward than the other way.
We tried with honesty. You can add or subtract like some sort of honesty vector or truthfulness or something like that. And it works both ways. And you can kind of measure this. We have it in this new version of the paper. But yeah, I'm not sure about languages. It definitely works. You can go both ways, but probably you would do damage by going, like giving that C++ is better, you would probably hurt performance going backwards.
Kind of the mapping from here to here is straightforward, like there's no.
Yeah, it's like many to one, right? Unless how does I don't know. I don't know. We haven't tested this. I mean, it's a good question, but I don't have, I'm afraid, anything intelligent to say about that.